Hello everybody, today I want to continue explaining about the star clusters. Let me share my screen. Yes. We have four star cluster parameters: reddening, distance, modulus, age, and metallicity. Determination in the order, reddening, age, distance, modulus, simultaneously, metallicity with possible iterations. You see here, we have a star cluster here, but we have some stars which we call them foreground and background stars. Now, today I want to explain you that how we can distinguish between the stars in the star clusters and foreground and background stars. As you see here, for example, you see that here, yes, it's main of the star cluster. But what about these other stars? Are they from foreground or background, or they are also related to the star cluster? Here you see the HR diagram for various open clusters and isochrons of them, young star clusters, also old star clusters. The oldest is M67 and the youngest is NGC 2362. Also you see here turn-off point, and for these isochrons we have them, and we can fix the isochron by reddening, distance, and age by free. Then we can go to metallicity. And also for this one, we can say we have parallax. Parallax means distribution, and by parallax we can measure how is the distribution which Gaia satellite does for us. And in galactic disk we have more stars, and in galactic halo we have less stars. And you see here turn-off point is a location where the stars, where the star cluster members leave the main sequence stars, or the main sequence, and we can directly correlate it with the age. Isochrons with the same reddening, age, and you see here. Isochrons with the same reddening, age, and distance and metallicity should fit the data of the sum diagram for all color magnitude diagram, or CMD, independent of which color we look at it. And in here you see color magnitude diagram for different color magnitude diagrams for one open cluster. You see in different classification. For example, these are related to Johnson photometry, and this is related for 2-mass photometry. And you see, for example, in Johnson photometry, you see these 3 stars, but in 2-mass you do, but in others where you do not see these 3 stars. Also, this 1 star you see here, but you do not see here this star. And so we can say we should have many photometric systems, because maybe there are some stars like this or this, some stars which they are not in 1 or 2 photometric systems. So we should measure all photometric systems. And we have two calibrations because of color. One is for giant and one is for main sequence and dwarf. For dwarf and main sequence, we have one photometry and one calibration. And for giants, as you see them here, maybe here and here, we have the other calibration. You see here different photometric indices, Johnson and Strongren and Geneva, Gaia, Tumas, and others. And we have also mixture of the photometric indices like Johnson U minus B, Strongren C1 and M1, and Geneva D, D, and M2 photometric indices. You see, we can measure theta, where theta is 50/40 over T effective, and we can measure them in here. C is color, B1, 2, 3, 4, 5, B0. They are coefficients. And we can measure them, for example, C color. We have, for example, also mixture of them, Gaia and Tumas and Johnson, as you see here. Mostly they are for Gaia. And number of stars and coefficients and the others. And we can say for each coefficient, we should have error to have them in more precise way. And here also you can see in different way color and coefficients, and we can measure coefficients and color to have the theta. And this is the, for example, final calibration. These are for cold stars in 5,000 T effective. You see the calibration of them. And here you can comprise with other calibration, comparison of them. For example, if you cut them, you see that for these two, their slope is the same, but in here you see it has some difference. And in here, Martin and his colleagues measure the photometric data with they assume also the error number, and they measure the coefficients with 6 decimal after decimal, 6 number after decimal, and you see that these are so precise. And how to derive cluster parameters? Use as much as possible available indices. Check the literature for published values at least as at the starting point. First, try it with a standard set of data. For example, you know about the Pleiades. Then you can start with the Pleiades, as you know them, and it's famous. And automatic procedures available, but be careful about them. What is reddening or extinction or absorption? All 3 words related to one meaning. It means that a measure how much light between us as an observer and the star cluster is lost because of the dust and gas between us, mainly because of the interstellar medium or ISM. And also we can say that the reddening depends on wavelength. So if we have reddening in red region, we should have reddening also in other regions too. And you see we have a differential extinction within one star cluster because of local environment. And I will explain about it later. Reasons for the interstellar extinction, as I told you, interstellar medium, light is scattered at the interstellar dust, light absorption, it is hitting of the interstellar medium, depending on the composition and density of the interstellar medium. Main contribution due to dust, simulations and calculations in Cardeli et al., as you can see. In here we have different way of observation. We have ultraviolet, blue, visual, red, infrared, and so on. And you see that we have in ultraviolet, we have more dust in ultraviolet. And in here we can say that the dust which we see in interstellar medium must have the size which is comparable to the other wavelengths. For example, here it is the size of the 4 up to 5 micrometer. And this computer and this dashed line is related to observation. And how to drive reddening without isochrone? Without isochrone, we need photometry and classification. If we know the spectral type or temperature and color, then we look up at the tables and compare it with mean color of the spectral type. The difference of the color which we observe of the star and the color which is in the table, that the table is from model of a stellar atmosphere, is the reddening. And you see the tables like here, we have the magnitude, and we measure them. For example, the difference between that we observe about the star and the number which is in the tables gives us the reddening. As you see, different tables. We have different tables and numbers. And in here, you see the frequency distribution of differences between the distance modulo drift from the UBV plus MK and UBV plus beta data. You can cut off as you like. And for reddening map, we can say that these are the map of the reddening. And we can say that if we have the coordinates of the star clusters, we can draw the reddening map. Without a spectral type, we cannot measure reddening. And this is the other way of that, galactic coordinates. And we need galactic coordinates and we need distance from sun for draw the reddening map. You see here, Hafner 18, and the age of that is 8 million years, which is a young cluster. And the different distance is 6,000 parsec. And you see some differential extinction within the cluster, for example here, and we cannot see outside of this extinction or reddening or absorption. And you see the differential reddening in young open clusters, that they are so different from each other. And determination of the reddening isochrones. From two temperature-sensitive parameters, the determination of the reddening is not possible. You need one other observational index. First choices, U minus B, X, beta. Normally, you only have V, J, H, K, and so on. You see, we have mostly reddening, differential reddening in young clusters, because in young clusters, as you see here, we have dust and gas, and so we cannot see outside of the differential extinction. And it makes our work a bit hard, because, for example, you see we have a star in F7, with this color and with this absolute or apparent magnitude, but with reddening we have shift. So, but the real star location is here. At first we thought that maybe it is in F7 color or 0.5, but the fact it is in A0 or 00 in color. So with reddening, we should be careful in young clusters because we have shift. And for drawing the reddening, we would need a spectral information. Without the spectral information, we cannot measure reddening. And just with color, we cannot. It's not true. And this is the reddening shifts, which shifts the main sequence by a value of this, as you see. Also here, reddening vector. And for 1, it is early type region, hotter than A5. And for 2, it is late type region, cooler than A5. Here it is significant effect due to reddening, no effect due to reddening in this region. And here no stars hotter than A0, as you see here for reddening. And in here we draw the isochrone between 0.1 and minus 0.5. 0.1. Most of the stars are in this region, and the isochrone drew in this region, which most of the stars are here. And here we can say that in ultraviolet region, we can have a good estimate of reddening. Ultraviolet observations give us the most precise value of reddening. We have stellar characteristics. As you see, with ultraviolet, we have more precise reddening, but with others, no. We can say we have distance from Gaia and reddening from ultraviolet region. Here we have distance modulo or distance modulus, and for apparent distance modulus, we have this one, V minus MV, or absolute magnitude minus visual magnitude. And for apparent distance modulus, we have V minus MV or visual minus visual magnitude and absolute magnitude minus visual magnitude, and this 0 it is not included the reddening. But if we do not have 0, it means that it includes the reddening. For example, here it includes reddening, in which is a V. So we have it in absolute magnitude, but for apparent magnitude, we just have V minus MV, and by 0, which shows that it is not included the reddening. Be careful, there is always a mixture in the literature. How to determine the distance modulus? Direct isochrone fitting, calibrate MV or visual magnitude directly via photometry and spectroscopy with known reddening and visual magnitude distance directly. Advantage is statistical sample. You see here, for example, we can say that it shows the distance and these are numbers. For example, we have 4 stars in 1000, between 1000 and 2000. And we have, for example, around 10 stars in the distance of about 500 parsec. Here is the histograms of the distance modulus, reddening and metallicity of the selected member stars of M67, which is the old cluster, with H beta measurements. The arrows, which you see, indicate the main values adopted for the cluster. Here you see for turn-off point, we need absolute magnitude and color. For age, we need reddening and distance modulus, and we can have it from turn-off point. But for reddening, we can use reddening maps, ultraviolet photometry, spectral type, and temperature. In here, we can see that turn-off point is where the turn-off point is located. In color or temperature, we need in color or temperature, and also absolute apparent magnitude or luminosity. And direct correlation with the age, difficult to define for young star clusters. First, classical method, just to look at the color magnitude diagram. Also in here, you see the turn-off point and visual magnitude of red giants here. And these are dereddened indices. Here is the isochrone of the age and visual magnitude. No direct error estimation possible. Possible to use for star clusters between 20 million years and 8 million years, which includes somehow the whole clusters, star clusters. Here it is also calibration of the bluest U minus B 0, which is dereddened on the main sequence in terms of age, log T. It is very precise method, possible to use between star clusters for between 20 million years and 300 million years. U minus B0 for cooler stars. And it is the older age is almost constant. Also here, It is not very accurate, but still very useful. It is very old diagram and never done for 2 mass and near infrared. And here we can calculate the isochrones, the calculation of theoretical isochrones, lines of age equal age is done with stellar atmospheres. Three parameters is metallicity, X, Y, Z. You know, X is for hydrogen, Y is helium, and Z is for the other elements. We have zero age main sequence and T effective and luminosity, and this is D redent, chemical and gravitational evolution, and T effective and luminosity. T absolute stellar atmospheres, which these two are related to physics. Absolute flux, folding with filter curves, colors, absolute magnitudes, and so on. Thank you for your attention and see you next time. Bye.